Hello, this is Basic Chemistry. We're in Chapter 9 on chemical quantities, and we're in Section 9.5 today on energy in chemical reactions. This is one of the most unexpected lessons that most people, when they're studying chemistry for the first time, did not realize that a chemical reaction is just as much about energy change as it is about the properties of the matter that changes. So if you remember, the matter, like elements, think of them as Legos, are in some compounds. So you can have blue and red Legos, or two reds and a blue Lego, and it combines with a yellow, and they all break apart, and then they reassemble in some other way. Okay, they either all come together, or they all break apart, or they all switch parts. Okay, there's different possibilities. So when we balanced equations, we simply made sure that all of the stuff that was at the beginning of the reaction is at the same at the end. Okay. Well, in this lesson, we realize that it's not just about elements. Okay, it's not just that the elements switch places. The energy is also either released or absorbed. Okay. Now, the easiest way that I can explain this would be if you think of the Legos again. Let's imagine that I've got two red and a blue Legos, and they're all connected. If you attach an amount of money that it takes to make that Lego, okay, so let's say I have a combination of two reds and a blue, and it costs me 75 cents to make it, all right? So to put those three Legos together costs me 75 cents. If I take them apart, I get the 75 cents back. So it's almost like the quarter you put in the shopping cart at Aldi. You put the quarter in, you use it, and then when you are done, the quarter comes back. You get the quarter back. So if it costs 75 cents to make a compound, all right, so two reds and a blue, that costs 75 cents. If I have one of those in a reactant and they all break apart, then I get my 75 cents back, and now I can spend it on something else. Let's say at the end, instead of two reds and a blue, I end up with two blues. All right, I'll have other things, but one of the products that I make is two blues. Well, let's say that it only costs 5 cents to make two blues. Do you see that I'm going to get money back from breaking apart my molecules that cost 75 cents, and then I have to spend money to make new molecules? So at the end of the day, I'm either going to have leftover money, okay, which will go out as heat, or I'm going to need to borrow some money from somewhere in order to make it happen. So if the reactants cost a total of $1 and my products cost a total of 50 cents, then I had an extra 50 cents that goes away as heat. So it's going to get hot. All right, so there's lots and lots of chemical reactions that are heat producing. So say a fire, you have natural gas, you burn it, that's a reaction with oxygen, that's all it is, it's reacting with oxygen, but it's also producing lots of heat. You can burn yourself on a fire, okay? Well, in this picture on this page, I've got cold packs, okay? A cold complex. All it is a couple different salts. And as you mix the salts together, what's happened is the products cost more to make than the reactants did. Okay, so let's say my reactants, I have $1 worth of reactants, but $2 worth of products. Well, I've got all the atoms I need to make the products, but I didn't have the energy. So where does the energy come from to store it in the bonds of the products? It comes from the environment. So it'll actually suck heat out of the environment, and what it'll feel like is that it's getting cold. It's getting cold because it's sucking heat out of the air. All right, the heat is coming straight out of the air, and that energy that's in that heat, that heated air or the heated water or the heated hand, your hand that's warm and now it's cold, okay, whatever it is, or your fever or whatever it is, that heat will go into the bonds of the products and be drawn straight out of the environment. Okay, so in this reaction, we're going to play with heat, either going out or coming in. So we call this the heat of reaction, okay? And it's called the enthalpy of reaction, or the enthalpy of heat of reaction, or the enthalpy of reaction. So I'm going to say that the enthalpy is the amount of money that it costs to make a molecule, all right? The amount of energy it takes to actually glue my Legos together. That amount of energy is called the enthalpy of that molecule. Okay, its enthalpy is its total energy that has to spend. Well, if I take all of the energy of the products, how much does it cost to make the products, and I subtract how much it costs to make the reactants, then I know whether I let off energy or absorb energy. Let's say that I've got $2 worth of products and $1 worth of reactants. All right, then I have products minus reactants. 2 minus 1 is 1. Okay, that means I have $1 of heat left over. Well, what happens if I have $1 of heat left over? It goes out and the thing gets hot. Okay, heat is produced. What if I had $1 of products but $2 of reactants? Well, 1 minus 2 is minus 1. Minus $1, what does that mean? It means energy from the environment had to come in order for you to glue those Legos together, and the test tube got cold because that test tube used to be warm, and now all that energy is gone, and so it's not warm anymore and it's cold. Okay, so some test tubes will get hot when you put chemicals together. Some test tubes will get ice cold. Some test tubes will get so cold that ice will actually form on the outside of the test tube. The water in the air freezes like frost against the test tube. Okay? Some will get so hot that you put two chemicals together in the test tube, and with no heat at all, it just starts boiling and bubbling. Okay? And it's hot, red hot. Okay? Because it had leftover heat, and that heat comes out. In an endothermic reaction, heat comes in, okay? So you have a low amount of cost for your reactants, you have a high amount of cost energy from the products, and that means in order to go from down to up, I need to absorb a certain amount of energy in order to put those Legos together, okay? This is called endo, meaning inside or into. The energy is coming into. So if you were to have your products high and your reactants low, then heat must be absorbed, and your delta H, okay? Remember delta H, we just talked about delta H being, I take the products minus reactants. If the products is high and the reactants is low, then I'm going to get a positive number. If you have a positive delta H, then that must mean that I've gained energy from the environment, and that's an endothermic. Thermic means heat. So the heat's going in, that's an endothermic reaction. So, for instance, if I add energy, which means that it's actually one of the reactants, energy is a reactant here. If I add energy, that's an endothermic reaction. Okay? If I let off energy, so if energy is actually a product, then that means I'm producing heat and it's getting hot, and I'm dumping heat into the surroundings. I'm dumping heat into the environment. So if delta H is positive, okay, products minus reactants is positive, that means that products must have been high, reactants is low. Where did I get that energy? It had to come in from the outside. That's endothermic. Heat was added, and you think of it as a reactant. It goes on the left. Exo means out of, like an exit sign. Okay, so if I have a lot of energy stored in the reactants, I only have a little bit of energy stored in the products. Well, where does the energy go? Here's a certain amount of energy. This is a lower amount of energy. That energy left, and this is exothermic. Exothermic went outside. So let's say this is 2 and this is 5. What would delta H be? Heat of products minus heat of reactants. So 2 minus 5 is minus 3. So if delta H is negative, then it's exothermic. I had more energy left over, and so it went out. That's exothermic. Also, your energy is shown here as a product. Okay, so if energy is a reactant, it's endothermic if it's on the left. If energy is a product on the right, then you're going to make that energy. It's one of the things you make in this chemical reaction, and heat will be released. So here's a summary. Endo, heat is absorbed, okay? And the heat goes on the left side. The energy is counted on the left, and delta H would be positive. Products minus reactants is positive, okay? Products minus reactions, 5, 3. 3 minus 5 is 2, so positive 2. That's endothermic, okay? Exothermic. Exo means out, so heat's released. It's a product, okay? So the energy would be considered on the right. You're making energy. So if you had lots of reactants and a little bit of product, and this were 3 and this were 5, then your delta H would be 3 minus 5 is minus 2. Okay, so if you have a negative delta H, then you have an exothermic and it's going to get hot. If you have a positive delta H, you have endothermic and it's going to get cold because the energy in the test tube and the air around it had to go into the bonds of those chemicals in order to make that product. So here's an example. Identify each reaction as endo or exothermic. All right, well, I've got 92 kilojoules as a product. So if I produced it, it went away. Okay, it's going away. This is exothermic. Okay, in B, I have 556 kilojoules of energy. It went into it. I needed this in order to make the product. If I didn't have this energy, this product would never have been made. That means it went into it, and that's endothermic. Here they just gave you a generic heat. You produced heat. If you produced heat, it dumps out. It was one of the products, so it goes out. So this is exothermic. So here's exo. This is endo. This is exo again. All right. Hope you're learning something.